Hi, everyone. Very happy to introduce our paper, 3D PPE, 3D Point Positional Encoding for Multi-Camera 3D Object Detection Transformers. First, we'll introduce our motivation. Recent works found that encodings based on samples of the 3D camera rays can significantly improve the quality of multi-camera 3D object detection. However, the mechanism of 3D position encoding, PE, in previous methods have not been fully explored. Besides, camera ray PE from ray direction only provides coarse localization without the depth prior, and the inconsistent embedding space for anchor and camera ray PE further hampers the effectiveness of the attention mechanism in the transformer decoder. Thus, in our work, mechanism of several PE in the surround view system is analyzed firstly. Then we propose 3D point PE with depth prior to localize the 2D feature, and it unifies representation for both image feature and object query. Here, we give the preliminary of positional encoding. As illustrated in Figure A, the simulated scenario with 6 cameras, only one traffic sign appears in front view. The distance is set as 10 meters, rather than other cameras. Different position encodings for this scene are listed in Figure B. PE-based PE is introduced in PETR series. It allows for the production of 3D position-aware features, and it obtains the 3D coordinate information from a set of points along the camera ray. In order to clarify what location information is encoded in 3D PE, we further explore the effectiveness of different depth bin numbers, discretization methods and depth range as shown in table. Surprisingly, the results turn out to be almost invariable under different settings, where the fluctuations of NDS, map and mate are smaller than 0.8%, 0.4% and 1.0% respectively. It gives an intuitive hint that the performance remains virtually unchanged through the separated 3D points sliding on the camera ray. If the sampled points can represent the direction of the camera ray, it already provides equivalent information to the PETR's 3D encoding. We further reduce ND to 1 with fixed depth D such as 0.2 meters, 1 meter, 15 meters, 30 meters and 60 meters respectively. As listed in table, smaller d leads to inferior performance. It indicates that the scheme of current PE is no longer camera ray, while on par result with camera ray is achieved when d is larger than 15 meters. The phenomenon above enlightens us that the PE in PETR with ND equals 1 represents a lidar ray. Determination of a ray direction requires 2 points. As the fixed lidar's location provides the start point of ray, thus we can determine lidar ray direction with 1 point. We calculate the discrepancy, dis, between camera ray and lidar ray with the cosine of their included angle. When DDLC and D increment, the discrepancy between camera ray and lidar ray is almost eliminated. This further demonstrates that when D is larger, the lidar ray will have a similar direction as the camera ray. Thus, the experiment results will be on par with the original PETR positional encoding even with 1 point. As for the 3D point PE with ground truth depth named Oracle 3D point, a significant improvement is achieved with 6.7% NDS, 10.9% MAP, and 18.7% mate respectively, which verify that the 3D PE encoded from precise 3D point location is the key to improve multi-camera 3D object detection. As a camera-only system cannot gather ground truth depth information, we introduce a lightweight depth estimation module to substitute for the inaccessible GT depth. The overall architecture of our proposed pipeline for method. The plot on the up shows intuitive illustration of surround view images, sparse point projection, local zoom of front view and detection result. In local zoom of front view, the 2 dense point blocks located in left bottom corner indicate the 2 car object in the front view. The plot on the bottom shows the detail component of our method. Inspired by BEV depth and PGD, we design a hybrid depth module that fuses the directly regressed depth and categorical depth with a learnable weight. This is the figure illustrates difference among camera ray PE, feature guided camera ray PE and 3D point PE. Performance comparison of 3D object detection on new scenes val set. This is performance comparison of 3D object detection on new scenes test set. Representative similarity comparison of 3D camera ray PE in PETR and Rs 3D point PE. The position is selected on the car object appeared in front view. Representative similarity comparison of 3D camera ray PE in PETR and Rs 3D point PE. The position is selected on the background.